Welcome back for another session. We're going to be talking about earth materials today, mostly the small scale things that make up rocks. Okay? So, in lab we will have looked by this time at the different minerals. This one was kind of a joke. Magnetite, if you don't know what it is, you should probably drop out of school. Okay, back to serious stuff. What's the difference between a rock and a mineral? The mineral is the pure substance. The rock is made up of minerals. It's what's called an aggregate. It's where you put a bunch of different minerals together and form the rock. So if we look at this one, this is granite. This is a rock. You can see the pink feldspar, the gray that's quartz, and the black, which is probably biotite or maybe some other dark minerals mixed in. Key point though is the mineral is the pure substance. The rock is the combination of different minerals. A mineral has 5 key characteristics. First, inorganic means it wasn't ever alive, right? It's not a living or fossil or anything like that. This is made out of inorganic material, not wood, for example. It has a specific chemical composition, such as Na, which is sodium, Cl, which is chloride. Sodium chloride makes up halite, which is salt, common table salt. Right? Specific chemical formula. It's natural, so something that's man-made doesn't count as a mineral, such as cubic zirconia. It's solid, so liquids like mercury don't count. It has a specific crystal structure. So quartz, for example, has a crystal structure, whereas glass doesn't. Okay? Looking at this picture, we've got 5 minerals that are really pretty similar looking. If you just look at them, they're kind of white or clear, and they all kind of look about the same. So how do you tell them apart? Well, we've done this in lab. So when you see a question about this on the test, remember, I don't want to know, well, that's obviously halite. What I want you to do is to go through the process of identifying them. So calcite, you check with acid to see if it bubbles, fizzes, right? Because calcite fizzes with weak acid. Halite tastes like salt. It is salt. Or if you're not willing to lick it, then you can look and see the right angle cubes that make up the mineral. Talc has sort of a greasy feel to it and is the key ingredient in gold bond powder. Gypsum is softer than your fingernail, and it's what drywall is made out of. And quartz is harder than glass. In fact, it's what glass is made out of, but it has a nice crystal structure that makes it even harder than glass. Special minerals, evaporites. This is the the pan in Botswana. Yeah, I butchered that title. This is a place where you get lots of evaporation of water. So evaporites form evaporated water. When the water evaporates, it leaves behind salt, so halite is one of those. It can leave behind gypsum, so gypsum is another evaporite. And in rare cases, such as in Bahamas, you may also find calcite being left behind as an evaporite. The silicates are particularly important because they form our most common minerals that make up the continents and the ocean bottom. So that's why we care about the silicates. They're all made out of silica tetrahedra. What that is the little thing you see right here where silicon is in the middle and oxygen is around 4 corners. Not quite like the Great Pyramids. They had a square base, right? It's a tetrahedra, silica tetrahedra. Well, you can take those things and you can have them disconnected, laid out, random place. And if you do, you have plenty of spots in between where you can put magnesium and iron. Those are mafic minerals, right? If you think about an iron skillet, it's dark and it's heavy. So those mafic minerals tend to be dark and heavy. The other extreme, we bond them together in every which direction. There's hardly any room for magnesium and iron. We call those felsic. Quartz and feldspar are examples. Those 3-dimensional bonds are super hard too, so remember quartz and feldspar are harder than glass. Mica is bonded in sheets, and amphibole and pyroxene in chains. Independent tetrahedra down here for our mafic up here, mostly silica, our felsic. Okay, how do you remember that? It's kind of tough. So one of the stories I want you to know is about my dad. It's also written up in the book. Dad had a heart attack 2 years before I was born. He was an older father, but still, he was only 42 when he had his heart attack. He'd been in the Army, came home. He and Mom raised chickens, pigs. He'd eat a stick of butter and half dozen biscuits, half dozen eggs. Not a healthy diet. Ended up having a heart attack. So he was put on a really strict diet. Mom took it super seriously. And so one of the things she would do is if there was any fat in the meat, she would boil the meat, cool it, skim off the fat, and so that Dad would be eating the pure meat without the fat. Well, think about the meat and the fat and the way we separate that out. It's separated out based on density and melting point. The fat's light in color and the meat's dark in color. So if we look at this chart, thinking of the felsic as the fat and the mafic as the meat, the density, the fat floats. So low density. High density for the meat sinks. Melting point, the fat melts easier, it has a lower, so lighter, lower density, lower melting point. Color, the fat is light in color, the meat's dark in color, so lower, light. That'll help you remember that. You'll see the same chart on the test, no doubt, so learn it. Intermediate, we haven't really talked about much, but it's just exactly like it sounds, in between felsic and mafic. All right, it'll turn out to be more important when we start talking in the next section about plate tectonics, and subduction zones in particular. We should also mention some common non-silicates. They're important for human beings, really. So carbonates make up most of the rocks we live on top of here in Dubuque. Limestone and stuff are made from the mineral calcite, right? Oxides are a combination of metals and oxygen. That's where we get a lot of our ores for metal. Pure elements, copper, diamond, right? They're important for conducting electricity, for giving his presence to our prospective bride, whatever like that, right? Sulfates include gypsum, which you make drywall out of. Sulfides include galena and fool's gold, which is pyrite, right? Which is galena is where we get lead from. And halides includes halite, which is a salt, right? So all these things are important to human beings. They're not as common for rock-forming minerals as the silicates, but we still need to know a little bit about them. What are minerals made out of? They're made out of basic elements: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluoride, etc. Right? So look at those pure substances, combine the atoms together, the elements, to create something that, well, if you put together sodium, for example, with chloride over here, you get salt. Sodium in its pure form is an explosive metal. Chloride forms a gas, chlorine gas. But put them together, you get table salt that you eat every day, right? You bond those atoms together in four main ways. Sharing, which is covalent. Giving from one to the other, which is ionic. Kind of loose arrangement, which is metallic, and then weak intermolecular bonds. So here we have for the covalent an example of a water molecule where you have the oxygen and you have around the outside the elements being shared in the outer rings of the hydrogen and the oxygen. Here we have sodium and chloride for the ionic. Chloride is much bigger and it has one extra space in its outermost electron shell, which gets occupied by the electron that's given away by the one that's all by itself in the outermost shell of the sodium. Giving it away, this extra electron makes this ion negative. This one gives away the electron, becomes positive. Opposites attract. So the traction of these oppositely charged ions bond them together. Something like copper, the electrons aren't held in any one place very strongly and can float around from place to place. If we stick in electrons on this end, they come out on the other end. We call that electricity, right? Copper conducts electricity. And then if we think about mica or graphite, within the sheets they're strongly bonded, but between they're weakly bonded, so we can flake off that graphite onto our paper when we're writing with a pencil, or we can separate those sheets of the mica. Another kind of bond, not a mineral bond, but a bond between water molecules, is called a hydrogen bond. I didn't make up the title, but we're stuck living with it. Key idea is this: water is not like a barbell. It's at an angle, right? It's got the oxygen, it's got on the end of it the hydrogens, but the oxygen's a lot bigger. So in those shared electrons of the covalent bond we just looked at, the oxygen end of this molecule becomes a lot more negative. The hydrogen end becomes more positive. So notice you have an ion here, sodium, Na. We've dissolved salt in water, haven't we? So that dissolved sodium, notice that the hydrogen negative end is towards the positive hydrogen ion, and the negative end, the negative chlorine is towards the positive end of the water. Notice the difference in the water molecule here, the way it's oriented, versus the water molecule here. So what does that matter? Well, it turns out water's pretty amazing stuff. When you stick a paper towel into it, the water will rise up the paper towel. That's pretty astounding, isn't it? It's going against gravity, right? It's called capillary action. The frozen form, ice, is lighter than the liquid form. That's unusual for a substance. Ice floats, allows the little things to live down underneath it, right? The water bugs can walk on top of it because it has surface tension, right? That's pretty cool. And then water dissolves lots and lots of stuff. It's called the universal solvent because it dissolves so many different things. All these things are properties of this nature of water as a polar molecule, which creates hydrogen bonds. Okay, that's enough for right now, but keep in mind the way in which atoms of different elements bond together to create the minerals, and the minerals form the rocks. If you can get these ideas stuck together, connected to each other, you'll remember them a lot better.